So we're moving on now to marine corrosion. Professor Philippe Refait is the chair. He is professor at the Laboratory of Engineering Sciences for the Environment at the University of La Rochelle in France. His scientific interests are corrosion of steels in natural environments, biocorrosion, corrosion in the marine environment, cathodic protection.
Thank you, Charlotte, for this kind introduction. So welcome everybody to the marine corrosion session. So I'm working in La Rochelle. It's a French city located on the Atlantic coast. It has 3 seaports, including a large commercial seaport and a marina with more than 4,000 boats. So in our local university, most research axes are dealing with ocean and sea, and in our laboratory, marine corrosion is then one of the main addressed topics. Marine corrosion is a very ancient topic, if I can say, because humankind has, from antiquity, struggled with the corrosiveness of seawater to exploit the natural resources of the sea. I remember a museum in Italy where remnants of Roman wrecks are exposed. And you can see that, let's say, remnants from 600 years before Christ, the planks were fixed with an association of iron nails and copper washers. And of course, these iron nails are very, very corroded. And you can see that 3 centuries later, the Romans used copper washers associated with copper nails. So I don't think they understood what was galvanic corrosion, but whatever they managed, they found a solution to this problem. Marine corrosion is also a wild topic because it combines chemical, biological, and mechanical factors. And you will see through the program of this session that a great variety of research axes can be addressed. Finally, I also wanted to say that marine corrosion is a modern topic, noticeably because the recent and necessary development of marine renewable energy devices that has motivated innovative research. As you all know, it is also required now that anti-corrosion methods are environmentally friendly, and this also has led to a lot of modern research topics. Now I would like, and it will be a pleasure, to introduce the first speaker, my colleague, Sébastien Touzain. He works in the same lab as me, the LASI laboratory. He mainly works on organic coatings, and in particular on anti-corrosion paints. And its talk deals with thick marine epoxy systems. Sébastien, it's up to you.
Well, thank you very much, Philippe. Good morning, everybody. So, as you know, the sea is a potentially huge source of energy, but the development of marine renewable energy technologies able to harness that energy is at a relatively early stage. In fact, part of the problem is that seawater is an aggressive medium and metallic structures are submitted to corrosion. So, of course, we need some robust organic coating systems to protect against corrosion, but they also have to be tested. And so that was part of the ADUSCORT project. It means the improvement of the durability of structures with respect to the corrosion phenomena and biofouling. The aim of the project was to develop knowledge about corrosion mechanisms and their treatment in order to improve the durability of MRE structures. We had many work packages in this project, but this work is focused on the performance evaluation of different protection systems using different methods, including accelerated and/or normalized tests. So we had three different systems in this study with commercial paints that were applied onto steel panels. So the first system, which is called organic system, ROX, is constituted by two organic coats onto the steel substrate with a total thickness of 500 micrometers. We've got the third system, second system, which is the galvanized system, called RG, and of course we have the hot galvanized layer with 200 micrometer thick and three different coats with a total thickness of 500 micrometers. And the third system, which is called RM, is so a thermal spray coat, zinc aluminum thermal spray coat with three different coats with a total thickness which is about again 500 micrometers. So as you can see on this picture, we've got the coated panel, which is connected to an electrical wire for electrochemical tests, and the connection, of course, is embedded with a PU resin. So now the aging conditions. The first one is the immersion in the natural seawater in the harbor of La Rochelle. As you can see, we have a platform here where the panels can be immersed, and regularly, of course, we can take off the panels from the platform and brought back them to the lab for evaluation using electrochemical impedance spectroscopy. We also have some tests in the lab. So this is the immersion in sodium chloride solution at 35 degrees C. We've got 3 defect panels, which are immersed in an aquarium. So 6 identical panels for all the systems. We also have some X-cut panels that will be evaluated using the degree of corrosion, the measure of the degree of corrosion. So these X-cut panels are a scribe, which is 1 millimeter thick, 1 millimeter wide, sorry, and that was performed with an alcometer apparatus. And of course, because the substrate are not the same, we have a zinc coat or not, all the panels are put in different aquariums. All the systems have a separate aquarium. And now these are the cyclic tests, the cyclic aging tests. We've got the cyclic neutral salt spray, which is actually, this is cycle A. It means 2 hours of salt spray at 35 degrees C, then 4 hours of a dry period with a relative humidity between 20 and 30% at 60 degrees C, and then followed by a 2-hour humid period with a relative humidity which is higher than 95% and with a temperature of 50 degrees C. So in the cabinet, we've got the 3 defect panels, and EIS measurements were realized every week. But after this initial period in the salt spray cabinet, the panels were taken off the cabinet, and then they were immersed in the sodium chloride solution at 35 degrees C. And then they were evaluated using EIS. This was done in order to see if the salt spray period could have an effect on the barrier effect for a further immersion test. Of course, we also have some X-cut panels that were evaluated using the degree of corrosion. And finally, we've got alternate immersion test. It means immersion in a sodium chloride solution for 5 days in a climatic chamber for thermal cycling. It means 24 hours at 5 degrees C, then 1 day at 50 degrees C, 1 day at 5 degrees, 1 day at 50, and 1 day at 5 degrees C. And then 2 days in a climatic chamber at 50 degrees C and a relative humidity of 98%. we tested some free defect panels that were evaluated using EIS, and also X-cut panels that were evaluated using the degree of corrosion. So for EIS measurements, we use gamma equipment. The frequency domain was between 200 kilohertz and 50 millihertz, with 11 points per decade, with an amplitude perturbation of 30 millivolts at the free corrosion potential. It is important to note that the free defect coated panels with the PTC1 cell were first placed in an oven at 35 degrees C for at least 30 minutes before EIS measurements, in order to be able to compare the panels that were aged in seawater with a different temperature than the panels that were aged in the lab at a temperature of 35 degrees C. So with this EIS measurements, we were able to evaluate the water uptake thanks to the Brasher-Kingsbury relation. And with the low frequency impedance modulus, so typically at 100 millihertz, we were able to evaluate the barrier effect of the coating systems. But here, it is also important to note that this impedance modulus in the low frequency was divided by the coating thickness, because all the panels don't have the same thickness of course, when they are prepared. So in order to compare all the systems and all the panels, we used this parameter, which is called now the reduced impedance modulus. So impedance modulus reduced by divided by the coating thickness. And we have also the degree of corrosion for the X-cut panels, so according to the ISO standards. So we took some photograph with a microscope camera, and we realized the picture analysis using the software ImageG. So these are the results of typical results for the ROX system, the panel 5, so ROX 5, for the immersion at 35 degrees C. As you can see, we performed some EIS measurements every 1 hour for 50 hours. We've got a typical RC behavior, and we can observe a decrease of the low frequency impedance modulus. This is a rapid decrease, of course, of the barrier effect due to the water penetration into the polymer network. So with this raw EIS data, we are able to evaluate the water uptake value. So here on this first plot, on the top, you can see a rapid increase of the water uptake, of course, because of the water penetration into the coatings. Then a plateau, like quite constant plateau, about 3.54%, and then slight slight increase of the water uptake value for immersion longer than 26 days. So I won't discuss further this water uptake increase, but we know that this may be due to the paint delamination or the water that is present at pigment polymer interfaces, or eventually swelling. We can also look at the reduced impedance modulus. As you can see, in the first hours of immersion, we have a rapid decrease. This is of course due to the water uptake, and afterwards we've got a quite constant value for this parameter for more than 1,000 days of immersion at 35 degrees C. that was for the ROX system, so it means only organic coatings applied onto the steel. Now the results for the RM system, it means organic coatings on the thermal spray, zinc aluminum thermal spray coat. We've got similar results with a rapid absorption of water, then a plateau at about 4%, and then a slight increase of this parameter. And if we look at sorry, I used the pointer, it is better. Yeah, and if we look now at the reduced impedance modulus, we've got the rapid decrease and then a quite constant value all over the immersion period. Now the results for the RG system. So remember, this is organic coatings that were applied on galvanized steel. We've got the same water uptake value, rapid water uptake, and then a plateau about 4% and a slight increase. And for the reduced impedance modulus, we've got the rapid decrease and a quite constant value for more than 1,000 days of immersion. So the first thing we can say is that we've got finally similar water uptake value for all the systems. This is not quite surprising because we've got the same paints. They are only applied on two different substrates with a zinc coat or not. So this is okay. This is not so surprising. We can also observe that we have a higher barrier effect for the RM and RG systems. So maybe a better adhesion of the coatings, but more importantly, we have no significant degradation after 26,000 hours of immersion at 35 degrees C. Now, these are the results for the panels that were immersed in natural seawater, and they are compared to a typical curve, which is in blue here, that was obtained during the immersion at 35 degrees C in lab. As you can see, for the ROX system, we've got quite similar value. But for RM and RG, well, the value obtained here for the immersion in natural seawater seem to be quite lower than those observed with the immersion at 35. Of course, we can think about the effect of temperature, because we know that in natural condition we have temperature variation and maybe so an effect of the natural thermal cycling onto the metallic organic interface for the RM and RG systems. Now, these are the results of the free defect panels in the cyclic neutral salt spray. So during the first 60 days in salt spray, as you can see, the barrier effect doesn't vary. It is quite constant. There is no evolution of the barrier effect, no evolution of the reduced impedance modulus. This is true for the three different systems. In fact, we think that the dry period at 60 degrees delays the water uptake effect, and there is no decrease of the barrier effect. But after the test in salt spray, the panels were immersed in the sodium chloride solution at 35 degrees C, and then we can observe continuous decrease of the reduced impedance modulus, showing a decrease of the barrier effect. And this decrease seems, however, lower than the one that was observed in the aquarium at 35 degrees C. This is true for ROX system and RM system. But for RG system, we've got the similar values of the reduced impedance modulus, showing that maybe here RG was more sensible to this immersion in solution after the salt spray. So maybe RG is more sensible to thermal cycling. Now, these are the results for the the alternate immersion test. So the free defect panels were submitted to this test. And as you can see here, the ROX and RM systems show higher values for the reduced impedance modulus than the values that were observed in the immersion at 35 degrees C. But for the RG system, we had a problem. In fact, we observed some blisters after 3,000 hours of this test. So again, for ROX and RM, we can observe that the dry period in the test seemed to delay the water uptake effect. And for the RG system, we've got maybe a system that is more sensible to thermal cycling. Now, these are the results for the X-cut panels that were immersed at 35 degrees C in the sodium chloride solution. So this is the corrosion degree, which is plot versus the time of immersion. As you can see here, we've got finally the ROX system, so only the organic coatings applied onto the steel, that show the highest value of the corrosion degree. So finally, the worst adhesion to the substrate. And for RM and RG, it seems that RM is better than RG, but we have lower values of the corrosion degree. So the conclusion here is that, of course, the system is better with a zinc coat, so a thermal spray coat or the galvanized coat. If now we look at the result with the X-cut panel in cyclic neutral salt spray, again we find that the ROX system is the worst one, but with RG and RM system, it is not possible to differentiate between these two systems. The RM and RG are better than ROX system, so again it is better with the zinc coat, but we cannot differentiate the two systems. And one thing which is also important is that this test in neutral salt spray is more rapid than the previous one in a solution at 35 degrees C. Now the results for the X-cut panels in the alternate cycling. Again, this is a test that is rapid, more rapid than the immersion at 35 degrees C. We find again that the ROX system is shows the highest corrosion degree values. But now it is possible to have a difference between the RG and RM system. And in fact, we had to stop the RG, the test for the RG panels because we observed some delamination of the coatings in this test and quite rapidly. So again, it seems that here RG is more sensible to thermal cycling and is more sensible than the RM system. So this is a summary of the results. So just to remind you that with the immersion at 35 degrees C, we've got a water uptake value, which is about 4% for all the systems, but no significant evolution of the barrier effect for more than 1,000 days of immersion. For the immersion in natural seawater, for more than 1,000 days, we had a lower barrier effect than immersion at 35 degrees C. Maybe this is the effect of the natural thermal cycling. And for cyclic and neutral salt spray and alternate cycling, we had the same observations. The dry period delays the water uptake effect, and RG system seems to be more sensible to the thermal cycling. Now for X-cut samples, the immersion at 35 degrees C showed that the RM system was the best one. Same thing for the cyclic neutral salt spray. It is better with the zinc coat. But more importantly, the alternate cycling was the only test that was able to differentiate between RM and RG systems, with again the conclusion that RG systems was more sensible to thermal cycling. So as conclusion, It could be said that the immersion tests at constant temperature are not able finally to differentiate free defect systems with high thicknesses, up to 700 micrometer. So if we want to use this kind of test with a constant temperature, of course, lower thicknesses are needed to see an evolution of the barrier effect. The second conclusion is that the dry period in cyclic tests delays the water uptake effect with free defect systems. So, of course, this is a realistic conditions, but it should be only used for X-cut panels to have an answer and a possibility to differentiate between different systems, the different behaviors. The thermal cycling seems to be the best condition to differentiate between different systems, and this is true for free defect and X-cut panels. And finally, in our study, for thick and highly pigmented coatings, the X-cut panels and thermal cycling were the best edging conditions to differentiate all the systems. So I would like to acknowledge Philippe Refait, my colleague, for the invitation to the Congress, and of course the organizers of this Congress. I would like also to acknowledge the students and postdocs who participate to the project, Victor, Jeremy, and Alexis, and all the partners of the project. Well, thank you very much for your attention.
Thank you, Sébastien, for this very nice talk. I don't see any question in the QA panel, but maybe someone want to. Yes.
Sheila here. Can I ask a very quick question to Sébastien?
Of course.
Sure.
Sébastien, this is Sheila from TWI, University of Leicester. You gave a very interesting talk on behavior of some of the very well-known coatings. I was wondering whether the use of sodium chloride as opposed to seawater has some bearing on what the real performance is likely to be.
Okay, your question is about the composition of the solution, right?
Yes, yeah.
Yeah, so you mean that maybe we should use a more realistic seawater instead of the sodium chloride solution?
Just a thought. I was just asking whether you thought about this, and there might be other reasons for using sodium chloride. So just wanted to know what was your thought behind it.
Well, only sodium chloride, because usually it is done like this, because we don't use all the salts that are in fact present in seawater, because electrochemically this is the same behavior than seawater from an electrochemical point of view.
Thanks, Sébastien.
I had actually the same question, because from the corrosion mechanisms point of view, in particular for carbon steel, it would be different working in seawater or in a sodium chloride solution. And I have a question about the difference you observed between RM and RG system. Have you an idea of the reasons why?
Well, actually, yeah. Of course it is a problem of adhesion, I think, but that was made by an industrial process. We do not we did not make this preparation, this surface treatment, so we don't know exactly how was the roughness, for example, and we just received the panels. Okay, so we don't know exactly what was the preparation surface.
Okay, thank you. So thank you again, Sébastien.
Thank you.
I will now introduce the next speaker, who is Dr. Shiladitya Paul from TWI, that is the Welding Institute, and the University of Leicester in UK. One of his main research topics relates to the metallic coatings. designed for protection against corrosion in marine environments. And this is the topic of his talk. Sheila, it's up to you. Thanks,
Philippe, for the invitation and the introduction, and thanks to the organizer for putting a very excellent program together. I'm Shiladitya. I'm the director of MATIC. MATIC is a Materials Innovation Center, which is a long-term strategic partnership between TWI and the University of Leicester. And in the center, we look at new materials development, characterization, performance, evaluation, and also modeling as part of the remit. We have got 2 academics, 4 staff, 7 or 8 PhD students, and currently we've got 6 plus research projects with a total budget of about £2 million. In terms of the people who work, and today I'm going to present results of some of the work actually done by my PhD students and postdocs. As you can see, we've got quite a few people working with us, and particularly worth mentioning 2 of the researchers who recently finished their PhD, Rosa working with myself and Philippe, and then Veronica, who also worked on thermally sprayed coatings. In terms of geographical location, I'm based in Cambridge, where the Materials Innovation Center and TWI headquarters are based. And we are in a very nice English countryside by the lake. So my office is somewhere around here. Today I'm going to talk about thermally sprayed aluminium. My main area of research for the past few years has been thermally sprayed aluminium, and I'm going to talk a little bit about what are the things one needs to be careful about when using thermally sprayed aluminium, and also give you a little bit of insight into the future research topics that we are looking at. As Sébastien mentioned, managing offshore corrosion is a major issue, which has been a major issue for oil and gas in the past, but I think in the recent years we have been focusing quite a lot on offshore energy devices, including wind and wave, and there are several areas within the structure that we need to be careful of and take into consideration when we think about offshore corrosion mitigation. So Sébastien talked about the zone where they tend to use quite a lot of these zinc aluminium with a painted layer on top, which is the atmospheric zone primarily, where you have got the rotor, nacelle, the tower. Then you've got the splash and tidal zone, where you get wetting and drying. And Sébastien also presented alternate immersion test, which is quite relevant to the tidal zone area. And then you have got the area where you have got constant seawater, where cathodic protection is fairly effective. And then you go down to the seabed and where you've got seawater and mud. So the various regions or zones within the structure may require various coating systems or corrosion mitigation methods. So I'm going to talk a little bit about some of these today. So in terms of the protection system, I said we use quite a lot of sacrificial anode or impressed current type CB systems for submerged zone. And we use paint as well, or a dielectric layer, to reduce anode consumption or the current drain from the anodes. In the splash and tidal zones, these systems, they don't tend to be very effective because you don't have a constant layer of electrolyte present in those regions. So you might need to think about barrier layers such as paints. And another alternative that I'm going to present a little bit more in detail today is thermally sprayed aluminium or TSA. But before we go into that, let's look into what thermal spray is about. So in thermal spray, the material that you're going to coat is in the form of a consumable. It could be powder or wire. You need an energy source, so could be a combustion source or could be an electrical arc. oxy-fuel or fuel, or electrical energy, which provides the energy for melting or semi-melting of the particles, powder or wire. And these are propelled towards the substrate, these molten or semi-molten particles. They hit the substrate, impinge, expand, and they form pancake-shaped splats, and you build up a coating as you spray your consumable. At TWI, there are quite a few spray systems where you can use different type of consumables, wire, powder. You can have morphologies, different morphologies of powders, as you can see on the screen here on your left. The source of energy could be, as I said, flame. So you can have wire flame or powder flame spray. You can have arc, electric arc. And one uses this quite a lot for thermal spraying of aluminum and zinc and alloys. You can have high velocity oxy-fuel. This is primarily used for carbides and stellite type materials in the powder form. The particle velocity is supersonic, and this produces quite a dense coating. We also have plasma. In case of plasma, we tend to use ceramic materials or materials that have very high temperature, very high melting point, and plasma generally creates 10,000 Kelvin or so temperature, which melts all the materials that we have used so far. So we tend to get different coating morphologies depending on the consumable and the type of power source we used. So here's a video of one of our research technicians and the spraying using a manual wire flame spray. This requires quite a lot of expertise and experience, and Andy has about 40 plus years of experience using some of these systems. So the coatings, the thickness of the coatings that Andy prepares comes out to be very, very uniform. And this is, again, I said, requires a lot of experience. In terms of arc spray, this is a typical video of one of the arc spray process, twin arc arc spray. This is mounted on a robot, and you can see that we can have very good control in terms of the angle and the coating thickness. One of the important things for thermal spray is surface preparation. And Sébastien did talk a little bit about the importance of surface preparation. I'm going to delve into a little bit more detail on this topic. There are different approaches that we have used. There was a project where we looked at the angle of blasting and angle of spraying. So you can see that we looked at 80 degree angle for blasting and 90 degree for spraying. We also looked at various other blasting and spraying angles, and I'm going to talk a little bit more about the results that we have seen. So this is the result of the work where we looked at the effect of spray angle on TSA addition using test dollies, pull-off addition test dollies. On y-axis, you have got the addition in megapascal. X-axis, you've got angle, the spray angle in degrees. So we can see that between 30 and 90, we didn't see much variation in terms of the effect of spray angle on adhesion. It stayed around 22 to 25 megapascal, which is very typical for arc sprayed aluminium. When we looked at the spray distance or the effect of spray distance, so again, here you can see adhesion on the y-axis in megapascal, spray distance in millimeters. So this is a standoff distance of the gun from your substrate in millimeters. And here again, we can see they vary between 20 to 25 megapascal in most cases, which is also very typical for thermal spray, arc spray aluminium. So what these two results show is it's really not very sensitive to the blasting and spraying angle, the addition of TSA, which is quite useful to know, because when you're doing manual spray, your angle, blasting and spraying angle can vary, and you may not have that much control, especially for for edges and corners or bends, and this gives us some confidence in terms of the additional value that we might get for such systems. In terms of other factor related to surface prep, one of the things people worry about a lot is related to surface chloride contamination. And we looked at this in fair bit of detail a few years ago, used one of the ISO standard 8502 to look at the effect of salt, surface salt contamination. So as received blocks of steel, we had about 5 to 7 microgram per centimeter square. We grid blasted it to SA3, and we had typical values of about 1 to 2 micrograms per centimeter square. And then we doped these surfaces with different levels of chloride. And what we see here is adhesion value of the TSA coated surface. So TSA was coated on top of the surfaces with the known amount of surface chloride content, which is here in the x-axis. This is microgram per centimeter square. And what we see that for values which are below 2 micrograms per centimeter square, we are getting between 22 to 25 megapascal adhesion value. And the addition value decreases as we increase the surface chloride content. Not only that, we are also seeing the nature of delamination or disbondment that might happen due to pull-off. In this case, we are seeing that the coating has failed cohesively. And in this case, we can see that the coating has completely come off from the substrate at fairly high chloride content. Typically, one would want to keep the surface chloride content following NORSOC M501 to less than 2 micrograms per centimeter square. So that's a little bit about the effect of surface preparation and what are the things we need to be careful about in terms of surface. Now I'm going to talk a little bit about corrosion mitigation using coatings. There are a couple of philosophies that people generally talk about when they are looking at thermal sprayed system. One is use of sacrificial coatings, where if there is a defect in the coating, you still get protection of the substrate because the coating itself is preferentially corroded, which is the case for aluminium, zinc, and similar systems. And if you want to have a noble coating, things like nickel-based systems on steel, then if there is a defect in the coating, then your substrate would become the anode and get preferentially corroded. So that is one of the things that we were thinking about when we looked at various coating systems. And as you can see in this very rudimentary galvanic series, I mean, stainless steel active passive, this should be separate. However, this is just to show that we have got the galvanic effect coming into play when you're using things like aluminium and zinc. And the other thing to note is within the pH domain of about 5 to 8, 9 or so, there's a passivation region for aluminium. It might cause a bit of an issue because if you have passivation of aluminium, then essentially you may not be able to protect your steel if there is a damage at a later stage. That's why people tend to use activating compounds containing indium and magnesium and such like to make sure that you don't reach such levels of passivation. In terms of the kinetics of corrosion of aluminium in different pH regions, we can again see that within this pH range, we have got a fair bit of stability and very low loss or corrosion rate. So we are seeing that between 4 and 9, pH values of 4 and 9, we see very little loss of aluminium. And knowing that the pH of seawater is about 7.8 to 8.2, we can be certain that aluminium is going to work in this system. So the self-corrosion of aluminium is very low, but what will happen when it is in galvanic contact with iron or steel? So I'm presenting a schematic of a classical diagram, which people use quite a lot. Here we have got the anodic and cathodic branch of carbon steel. Similarly, we'll have the same for aluminium. So you can work out the corrosion rate, cell corrosion rate of carbon steel and Igor value for those. Similarly for aluminium. And when you bring them in contact, galvanic contact, you get a mixed potential. And by extrapolating the anodic branch of carbon steel here, you can find out the reduced corrosion rate of carbon steel. And you also get the enhanced corrosion rate of aluminium that might happen. So we have established that the self-corrosion rate of aluminium is quite low, and we have also established that aluminium would protect steel in various environments, in various pH. So let's look at some of the performance data that we have generated over the past few years. So because this work was done a few years ago, we followed the ISO 20340. This has now been replaced by 12944, but the test procedure is still the same. So we looked at two different systems. One, a steel coupon with a paint layer. So again, this is a two-layer system. In case of TSA, it was just a TSA thermal spread aluminium layer of 300 microns thickness. We created a scribe. So this scribe is about 50 millimeters in length with a width of about 2 millimeters. And this went all the way through to the substrate. So the steel is exposed in both cases. We subjected these samples to 25 cycles of 7-day cycle each with a 3-day UV condensation at 60 and 50 for 4 hours each, followed by 3 days in ISO 12227 type system. Instead of using sodium chloride solution, which ISO 9227 suggests, we used synthetic seawater, STM-D1141, to actually replicate the chemistry that is there in seawater. And on the 7th day, we exposed the samples to -20 degrees. And we repeated this cycle for 25 times, which took about 6 months for completion. And what we saw in the painted system, the circles here, these are due to the adhesion test dollies. And the numbers, 7, 10 megapascals, these are the adhesion values that we obtained from the test. And these are the test dollies you can see here. So when we looked at the samples in a bit more detail, we saw that in the damaged region, we saw 1 millimeters scribe line was exposed. This was exposed steel, and we can see some rust formation, which is not surprising at all, because these coatings, they act as barriers, barrier layers, and if there is a breach, then the corrosion is very likely. However, when we looked at the thermally sprayed aluminium system, we can see in the scribe region there is no rust. We only saw some white products formed. I'm going to talk about the products in a bit more detail in the next slides. And the adhesion values, even after testing for 6 months, is 18 to 22 megapascal, which is very encouraging. So when we looked at the scribe lines, we can see that the scribe, which had a steel surface, has got some corrosion product or product maybe from seawater deposited, and we wanted to look at this in a bit more detail. So when we looked at the backscattering electron image, we can see that there are two different compositions and morphologies, one closer to the seed substrate and one away from it. So the layer away from it was predominantly comprised of calcium, and we could also detect carbon and oxygen peaks. In case of the layer close to the seal substrate, the darker region here in backscattered electron images, we can see it's predominantly magnesium, and we also detected oxygen in these layers. When we looked at these layers under SEM, we confirmed that the layer close to the seal substrate is magnesium hydroxide or brucite, and the layer away from it is predominantly calcium carbonate or aragonite in this case. We also wanted to look at what happens when you have larger defects and higher temperatures. So we did the same experiments, but with a more controlled defect area here, 20 millimeters in diameter. And we did the test at various temperatures. I'm going to talk about the 5-degree and boiling seawater in this presentation. So what we saw at 35 degrees, which was another test we did, is again, the corrosion rates, they are a function of time. And after 250 days or so, we did this test for over a year. After 250 days or so, we found that the corrosion rate got down to a few microns, 3 to 5 microns per year in this case. And in most cases, we are still seeing that TSA is able to polarize steel to well below the so-called productive potential of minus 800 millivolt or so. When we looked at the other temperatures, 5 and 101 degrees Celsius, boiling seawater, again, we see that in both cases, we are below the productive potential. There's a difference in the potentials at 2 different temperatures, and we expect that from nonce type behavior. And we also saw the corrosion rate in both cases were still below 20 microns. In most cases, maybe around 10 to 15 microns or so at the temperatures of 5 and 101 degrees Celsius. When we looked at the samples, again, you can see on your left, it's before nice and shiny steel surface, and after we get some white deposit. We cross-section these samples, and at 5 degrees, we found that there is a very, very thin layer of magnesium hydroxide close to the seal surface, and we have got a lot of calcium carbonate above it. And at boiling seawater at 101 degrees Celsius, most of the sample is covered with magnesium hydroxide. There is no calcium carbonate. And we looked at the mechanism in a bit more detail. And at boiling seawater, because we don't have CO2 solubility, we are not seeing calcium carbonate formation. And at room temperature, we also looked.
Sheila, be careful. Only 2 minutes left.
Yeah, sure. So we looked at the cathodic reactions in a bit more detail, and Philippe and I, we published a paper, Rosa's work in corrosion science recently. I can give you more details a bit later if you want. We also looked at higher temperatures, and this was done at 500 bar in air for 30 days, again using synthetic seawater at 5 degrees. And what we saw is, in this case, we predominantly have magnesium hydroxide with some specks of calcium carbonate forming. We didn't have electrochem because at those pressures we didn't find a probe that will work, but we tried to find out some indication of corrosion rate based on the amount of dissolved aluminum iron. We know that this is not the real corrosion rate, but we had some good idea in terms of corrosion. So we can see that corrosion rate of carbon steel was decreased significantly by using TSA. And we try to understand the effect of pressure by looking at the solubility of different compounds. And I think the change in solubility as a function of pressure could be the key for this. And we want to do a bit more research on this topic in future. So in terms of the current and future research, we are looking at whether TSA would protect high-strength steel from hydrogen embrittlement. Where does the hydrogen go? This is a co-research program, or CRP. We are looking at how much damage TSA can tolerate, as a part of a collaborative project. We are also looking at TSA in conjunction with applied CP and how TSA can work in presence of a sealant and whether TSA would mitigate biofouling and such like. So there's quite a lot of research ongoing. I'm happy to discuss more offline related to that. So in summary, I talked a little bit about TSA. Although TSA works fairly well in several environments, but we have to make sure that we follow the right procedure in terms of surface preparation and make sure that we have the right Q&A in place for use of TSA in service. And thank you very much for your time.
Thank you, Sheila, for this very nice talk. We have a question in the conversation about I think it's about the composition of the thermally sprayed coatings. It's a question about aluminum magnesium alloy. Have you?
Yes, we have actually used aluminium 5 magnesium, which is typically something that the Norwegian industry has been using for a while now. I didn't present that result because I wanted to talk a little bit more about the aspects related to TSA as such. But yes, aluminum 5 magnesium in terms of performance, we have seen very similar results to the 1050 alloy that I talked about today. And we have actually published a paper in NACE last year. So if you want more details, do get in touch with me. I can provide the paper.
Yeah, thank you. And I have one question. It's another question about the medium you used. So you mainly present results in artificial seawater. What happened in natural seawater? Because there are some differences, in particular the biological activity. Have you some?
Philippe, this is a very interesting question, and you and I both know that there's a difference. And we had a student, Rosa, who worked with you and I and did some tests in natural seawater, and we see quite a lot of marine growth in the samples. But in terms of the sacrificial protection behavior, I think we still see that is active even in natural seawater. Okay.
There is an addition to the question about aluminum magnesium alloy. In fact, the person wants to know where the magnesium hydroxide comes from.
Okay, so I think in the slide I did probably show very quickly. Maybe I can just explain a little bit more detail here. So what is happening in natural seawater? You have already got dissolved magnesium and calcium salts in seawater. So when you have TSA, which cathodically polarizes your steel surface, the cathodic reaction, which in natural seawater is the reduction of dissolved oxygen, gives you quite a lot of hydroxide ions. So locally, the pH increases. And due to the local increase in pH, the dissolved magnesium generally precipitates as magnesium hydroxide. So you get magnesium hydroxide irrespective of whether your TSA has magnesium or not, because the magnesium in this case is coming from seawater, not the coating.
Thank you. So I think it's now time to, thank you once again, Sheila. I think it's now time to introduce the next speaker.
Thank you, Philippe.
Dr. Igor Chaves is a senior lecturer at the University of Newcastle in Australia, and he works mainly in the domain of civil engineering. And as you will see, his talk deals with the effects of marine atmospheric corrosion on coastal masonry veneers and cavity brick walls. Igor, it's up to you.
Thank you, Philippe. Good evening, good day, everyone. So, hello from Australia. So I'm coming a little bit of a left field here amongst you all experts in corrosion science and electrochemistry. As a civil engineer, I mainly focus on long-term, decades-long implications of what corrosion may or may not do to our infrastructure. And as you can see by the photo there are some problems to look for. This is an unfortunate recent case in 2017, relatively recent, I guess. There are more examples in Australia and unfortunately in other countries as well. But I'll focus here on just a couple of background research that we have been conducting in regards to obtaining empirical evidence and quantifying information to allow the relevant regulatory bodies or governments and local councils to act in a mitigating way to prevent these sort of issues without blowing the budget, of course, particularly with other COVID-related pressures. But as a civil engineer, I just wanted to bring you the attention that sometimes it's easy to just be very focused on what we're doing and forget to step back a bit. So quite literally, this is a very overview photo of Newcastle. And the reason I'm showing this to you is for a few reasons. One is to highlight that there is significant industrial activity. The port of Newcastle is one of the world's largest coal exporting ports in the world. So there's heavy activity daily, 24/7. The infrastructure, as you can see, is not extremely tall. There's a good reason for that because of the soil conditions. But what's interesting is that most of the buildings are very, very old. So I'm going to guess here 50 or 60 years plus, majority of the Newcastle infrastructure that is currently used. Not just Newcastle, but Sydney and other cities in Australia and in fact around the world as well. But you're more than welcome to visit. As you can see, I'm quite biased, of course. Picked a nice place to live and study and work at the university. And in fact, Newcastle has been chosen as the host city for the 2021 Corrosion and Prevention Conference. So if you haven't heard already about the Australasian Corrosion Association event, you should look into it. There's a quick link there. I'll just give you a second to take a screenshot of this and you can look it up later. What I'll focus on is on the buildings we use, not the ones that are listed for demolition, but like hospitals, for example, that have been identified to having risk of collapse imminent. This is very recent news from the ABC, and it's a hospital. So what do? You stop the hospital, you put scaffolding up the wall and wave to the patients in the room. They'll enjoy that, I guess, based on the circumstances, of course. But my point is, if there is a corrosion issue inside these walls, how do you track it? How do you quantify it? How does the regulatory bodies make a decision based on a prediction, based on a formula? You could take bricks out. You pull the bricks out at certain places, and there are standard procedures for this. But how do you know where to look? The ties might not be there anymore. So basically what this photo here on the bottom left is showing you is that there are metal fitments inside the walls to hold two walls together so that they work structurally and the building is strong and efficient. But if you open up the wall, you might observe that not every single piece of metal is corroding at the same rate or at the same time or under indeed the same circumstances. So what are the mechanisms involved, right? Have you considered the spatial variability? Is there a certain microclimate forming? Are there cracks or any other environmental variables, sulfates and pollutants, or whatever other reason that could have caused an accelerated corrosion attack at a certain place? Is it just the elevation? Is it the north wall? Is it the south elevation? Is it the east and west, the one that's in between buildings and gets wet most of the year? You call in an expert and they go visually inspect. They look at it and, yeah, there's a problem there. How do we handle it, right? They look at this wall and said, yep, you got a problem. How do we sort this one out? Understanding corrosion morphology, where do you start, right? You're trying to understand what caused the problem in the first place and then reverse engineer a system to try to make an informed decision of where to invest your inspection money so that something like this doesn't happen. Yeah, you don't have a catastrophe. Mind you, these are small, short story buildings in Newcastle, but there are, of course, higher rise 12, 13 story masonry buildings in other cities in the country as well. Interesting enough, descriptive statistics is very scarce in the literature for this because simply there's just too many of them. It's difficult to inspect and get a realistic picture of the data. So that's what we set out to do. Now, let's just be diligent here and then just be clear. Yes, there are many faults and errors done, but we're just going to assume that even the buildings that were constructed and inspected to the letter don't present these sort of things. Yeah, so let's just assume for now that these errors won't happen. Of course they won't. Everybody does the right thing when constructing the buildings, right? The top left figure there is a fitment that was supposed to be connecting the two walls, and somebody just bent it up to make it easier to lay the bricks, right? And just forgot to put it back down. This is nothing new. There are existing systems and technologies and services in this case, as you can see by the middle picture. What can you do if a problem is identified? So let's just say the wall is reported to be loose and it's an imminent collapse, or you can visually see it bulging out of the building. So you call in a crew and they rappel down, very risky and very costly, take out bricks and inspect the ties. Yeah. There's also products available from the market, and you can readily just, again, rappel down the side of the building and drill these through the bricks. Hopefully you won't crack the bricks or the mortar is still good, and you can simply reconnect the two eaves, as they call it, to provide structural stability. I'll elaborate in a little bit because I know there might be a good proportion of you who are not civil engineers, but just bear with me. I just want to also mention that there are techniques and products and services that you could solicit that will be installed as the building is constructed. In this case here, just an example of a filler foam that you could be used to literally glue the two eaves together and give an air seal, tight seal to all the metal fitments in the wall. But I haven't checked this. That's what they're claiming. Yeah, obviously for a modest price, as they call it. So just to elaborate a little bit further on the corrosion itself, what are we focusing on itself is this is a typical brick veneer. So the veneer stands for this layer of bricks on the outside of the wall, or in this case, the one-story house or two-story house. And the bricks simply serve the purpose of protecting the timber frame that supports the weight of the roof and the whole structure. So in a brick veneer situation, the bricks are there to protect the timber. And they are vented both at the bottom through weep holes, which is important to release the accumulated humidity that occurs every day. And they're also vented at the top for expansion reasons. Yeah. And this wall is held on to the timber structure by these metal fitments. There is a standard that specifies how many of these fitments per square meter you should install to ensure stability. In older buildings, it's more common to have a cavity brick wall. And that means that there's now two eaves of bricks, also connected by metal fitments every so often. These are slightly different in shape, but they're also vented at the bottom, at the top. And they also have these large shafts connecting the roof structure itself to the internal eave. Yeah. The external eave, this one here, exposed to the elements, is purely to protect the internal wall against the elements. Yeah. So this internal wall here is the one that bears all the weight of the roof and the whole structure and takes it down to the foundations. Right. Just another picture here to help you visualize what I'm talking about. They're very, relatively speaking, small metal fitments. They're thin. The older ones are lightly galvanized, and modern brick fitments or wall fitments are made of 316 stainless steel by standard. Okay, so this is nothing new. People have been done a lot of work, and there are standards for this to specify what type of brick tie and material you should use and how often you should use it, depending on which environment you are to build in. So let's just start there by the Australian standard in this case. There's the European one, of course, but it's based, the Australian one is based on the ISO. So we have, in this case, for the Australian categories, 5 different aggressiveness, C1 to C5, as you can see here. And it's subjectively classifies the corrosivity as to very low. And it gives you an indication of the corrosion rate per metal, okay? Typical environment examples are also given here, as you can see. Once the exposure classification is defined, and this is done by a mapping zone, it's simple as looking at where you're going to build. That's your category. Jump into what type of R rating resistance you would need. So as you can see here, if it's a moderate certain situation, it's an R1, so just above 10 kilometers from the coast. An R3 marine is up to 10 kilometers from the coast, and severe marine is just basically right at the beach. Yeah. So based on this, we can then define the materials. So this is once more from the Australian standard, and it says for AS 3700 is the masonry construction standard, structural masonry. And you can see here that it gives you different types of material, hot dip galvanized, or stainless steel 304, or stainless steel 316, depending on how aggressive the environment you are building. And simply to ensure a decades long, in plural, service life for your wall. Yeah. So this is all well and good. We define the material, we put the ties in. This is for new buildings. And you just assume it'll last 50 years, it'll last 100 years. How much do you know? And this is assuming every single tie at any given point of the wall will last that long. Yeah. How can we be sure of that? Well, there's some smart people before me, and they've done lots of accelerated tests. And they've used the AS2699 from 2000. And it says there that if after a certain amount of hours in a salt spray, which is artificial seawater exposure during intermittent or continuous spray, there's a various way to do the test. But effectively, after a certain percentage of mass loss has been accumulated or quantified, you consider that the material to have failed its service, yeah? So just to give you an idea of what we're looking at. And then what? Then we try to predict what happens in real life, yeah? That's what it's for. This is just a generalization from the salt spray test. But then some very smart people, and in my opinion here, Dr. Hagel's work from Alberta Institute of Technology has been very good at trying to model this phenomenon. And in their work, they've used the ISO model and identified a number of different variables, as you can see they're listed on the slide, as to which would influence the most the corrosion rates that happen in situ. Yeah. From there, there's a different model that they elaborated on, and then uses slightly different variables, as you can see there, the pollutants from the air, and they take data from 13 different countries as well. So this is also relevant because different countries have different climate circumstances, different environmental circumstances, even local urbanization, right? Metropolitan areas would have a different climate environment compared to the coast and so forth. But this is what stands out to me in particular. This is just an extract from their work. And as you can see here on the table, there's a number of specimens, a number of repeats, and they've obtained empirical results in grams per millimeter squared per year. And the spread is quite large, as you can see. So 48 grams or 8 grams or 31 grams. Or you can see here as well from the ISO model predictions, you get 45 grams or 10. And here for the ISO model, different values once again. So I don't know about you, but I kind of scratched my head. I said, okay, well, let's just imagine you're going up to the mayor. The mayor asks you for an opinion, right? When is this wall going to fall? What should I do? Should I replace the wall? Should I inspect the wall? Right? What do I do? And then you go, let's just take the lowest number. Yeah. You're just going to assume, sorry, the highest number. Let's just assume you're going to take the highest number right here. And that's what you're going to base on. You calculate it. The wall is good for another X amount of years. Mayor saves up some money until then and then fix the walls. Yeah. Unfortunately, there are circumstances where this might not even be representable as well, because after all, this is just 9 samples out of one particular study. So how do we know? So this is what we set out to do, obtain information. So what I'm going to do now is I'm going to give you a few examples of in practice, in situ measurement. The lovely building there is literally down the road from me, and it's a heritage listed building, Newcastle City Hall. built between 1927 and 29. It's a 3-story stone-cladded building, okay? And the bottom right there shows you a brief sketch of the metal fitments used to hold and tie in the sandstone to the supporting structure. There's me and a colleague at the roof at the inspection. And basically what we found was that according to records, the original 8mm light galvanized fitments were still okay, as you can see there. And now, mind you, of course, there's some human error in measuring that. At that particular spot might not be 7.93, but you get the idea. For that building of that age, right? Once more, 1927, and it's very close to the coast, less than a kilometer from the sea, from the ocean. And they're fine, right? Mind you, there are cracks, and where there were cracks, there were water ingress, and then there's other corrosion products expanding and causing even more problems. So due diligently, we excluded these outliers, if you like. But ultimately, this is a very important building. So the Lord Mayor and all the council's wisdom, they decided this is a very important heritage building. We should protect it, and as we should. So we're going to spend a lot of the taxpayers' money on it because we can, and we're going to replace every single metal fitment and replace it to the modern standard requirement of stainless steel 316, and that's what they did. All well and good, right? Did the right thing. They inspected the building, they checked it. Yep, they made a decision. Let's spend the money now so that we don't have any regrets in the future. What happens if you know grandma or grandpa or a mate or a neighbor or someone that's a building owner that is an investor and has no idea of structural engineering or corrosion science, and they're not the mayor and they don't have the council. So what do they do if they're to maintain their building? How do they know? When is it going to fall over? Are they going to be sued by the tenants or the owners of the apartments? What's going to happen? So unfortunately, I'm not in the liberty of disclosing the details of this particular building as per request of the owners, but we also got to inspect a number of buildings in Sydney. And this particular one that I'm sharing with you is the 1960s. It's an 8-story residential building, and it is a load-bearing brick cavity wall building, meaning that the building itself is held up by brick walls. Yeah, all 8 stories of it, okay? The outer leaf, as you can see, is on the left-hand side of your screen, and the inner leaf on the right-hand side. The cavity has a certain width established, and the brick ties or metal fitments are there. Straight away, you can see that this particular example, there are some examples of some things that might be going on one end of the fitment, but not on the other. Maybe there's a gap here where humidity accumulated. For those who are not familiar with bricks, they basically are sponges, and they soak up humidity from the air, and they're effectively wet most of the time, particularly when in humid countries or in areas like in Queensland and Australia, in the tropical rainforest zone, it's wet for long periods of time. So that humidity can accumulate in the mortar and the brick itself, be then diffused through to the cavity. But my point here is, look at that. It's interesting. Once more, the outer leaf is on the left. You can see that there's definitely more corrosion occurring on the outer leaf side compared to the inner leaf, yeah? Is it on all of them, Igor? No, it's not. In some elevations of the building, it's a lot of work to inspect a lot of spots of the building. But there, I can tell you, it's very, very random at this particular point in time. So it might be a crack, it might be a loose brick, it might be just poor workmanship. It's just very scattered in terms of data. It's very hard to represent in real life what you do. So how do we do this? How do we come up with a representable model or empirical data that we were able to use to predict what happens into the future? Yeah. So that's what we tried to do, or attempted to do in this study. And a colleague of ours, Jardine, she's done, as you can see, hundreds and hundreds of samples over a number of years and tracking in detail the corrosion damage of these. She placed brick ties, as you can see, of different materials in different mortars. So we are trying to help the governments to make a decision on older existing infrastructure, right? Because if you're going to build a new structure nowadays, you just follow the new standard. Put the stainless steel, you're good. But what happens to the thousands and thousands of buildings that are already being used, that were built even before the standard was even published? How do they know those walls are good without spending too much money inspecting? So that's what we try to answer, yeah? So the mortars that we used for these experiments were threefold. The first type of mortar imitated or attempted to replicate the old style of mortar. Some of them prior to Portland cement, to be honest with you. So that's something we considered as well. So a number of different types of materials, a number of different types of mortar mixes, and they were exposed in two different places. One in Newcastle, New South Wales, which is on the southeast coast of Australia, and another lot at Perth, Western Australia. So now it's on the west coast of the country. So as you can see, we've put the samples right next to the beach, and they've been there for years. They were exposed in semi-sheltered racks, as you can see by the right-hand side photo. There were a number of them, and they were elevated from the ground so that we wouldn't have any problems with wildlife interfering with the experiment. And we wouldn't have any problems with the seagulls or pelicans leaving their, let's just say, remains on our samples and causing any adverse acidic reaction on them. And as well, we of course instrumented time of wetness, temperature, relative humidity, sulfates, and the wet candle chloride deposition concentration as well. Results. I know we're short for time, so I'm just going to jump straight into this. Basically, what I'm showing here on the photo is the result of what the sample looks like, or a sample looks like on the left when exposed to natural environment, right, at Newcastle, and the SEM image just to show you what it looks like up close. Now I'm going to show you the exact same thing after it's been exposed in the salt spray chamber. Now, mind you, it was a very aggressive salt spray chamber, so please keep that in mind. But straight away, you can see that there's a difference, yeah? If we plot the results, and this is coming from Jardine in 2018 preliminary studies, so 6 months data there, as you can see. The scale on the graphs are the same, and you can see there's already a difference, yeah, in terms of corrosion loss in grams per centimeter squared between the two different environments. Look, let's not get into details of the numbers. I think the main takeaway is that if we're going to do an exposed accelerated artificial test, it is just in its nature complicated to replicate exactly what happens in the real scenario in natural environment. Particularly speaking that in the artificial chamber, proportionally, there were higher losses outside the mortar, whereas in the natural environment, there were losses inside the mortar. This slide, I attempt to show you two things. First, the effect or possible effect. We haven't quantified this in detail just yet. Still crunching the numbers. It's a lot of data of the mass loss based on relative humidity. As you can see here, average humidity in the blue columns, and the temperature. So average temperature throughout 2 years, May to March. And as you can see, it fluctuated, and we tracked the losses over time. The green and yellow dots are an average mass loss for different types of materials. In this case, just the galvanized. So a Z600 is a 300 grams per square centimeter of, so less galvanizing, let's just call it that way to keep it simple, and the more galvanizing, yeah, hot dipped. So as you can see, sometimes there's no difference between how much zinc you put on it early on, but then it increases and then it drops again and then increases. Well, Igor, where's the error bars? What's the variability? Yeah, good question. Or you might be thinking, there's a lot of variability. But let's park that aside for now and look at something even more interesting. What about pit depth? So this is what the middle graph is showing you now. same thing, average humidity in the blue bars, and now showing you comparing the galvanized, the green and yellow, to stainless steel. Well, hang on a minute. If we have stainless steel in the building now, they're gonna pit, and then yeah, the losses are just as high as the galvanized one. So should we spend the money on the stainless? Scratch your head. Look, the price difference is not that great, so you might as well. But what about the older buildings? How does that work? And temperature, does it make a difference? Well, as you can see there, yeah, it has an effect. Maybe there's a combined or correlated effect between relative humidity and temperature, but I'll let you electrochemists elaborate on that, okay? Now,
Igor,
what matters? Yes?
sorry, Igor. Yeah, you're running out of time. I'm sorry.
Yep, I'm almost done. So as you can see here in the mass losses, we have mass losses versus wall ties comparing the galvanized to the stainless steel. So overall mass loss of the stainless steel is almost negligible compared to the galvanized. And compared to the previous model's predictions, the mass loss results we are obtaining are orders of magnitude higher compared to the previous model's prediction. So there's something going on there. And we're comparing this to the R2 class here, yeah? So 0.02 compared to 0.003 or 4. The pit depths, on the other hand, is quite relatable between any type of material. So it really just depends on what sort of corrosion mechanisms take place at a particular wall at a particular time. So what is the main takeaways? It's very difficult to correlate artificial and natural environments. We need to work on that. For natural environments, pitting becomes a main concern in the long term, right? Particularly for stainless steel ties, which should not be neglected. After all, if there's a hole in the middle of the tie and that breaks, it doesn't matter if it's still intact on both ends, right? It failed its purpose of holding the wall up. You got to be very careful when you're trying to generalize models. We're working on that, but we definitely need in situ data and lots of it to do it. We are continuously working to collect this data and elaborate the model. Thank you very much for your time. I'd just like to appreciate all the sponsors, the consultants, ARAP, and the Department of Industry and Building Regulations from the Western Australian Government, the Australian Research Council for financially supporting the research, and the City of Newcastle for allowing us to talk about the beautiful City Hall in the presentation today. Any questions?
Thank you, Igor, for this very interesting talk, dealing with a very unexpected and unusual topic. I have discovered a lot about building in Australia. There's no question in the QA panel, but if someone has a question, it's of course welcome. I'm looking in the conversation. No. I have a question. I was wondering all along your talk if it was really a problem of atmospheric corrosion, because in fact it's a very confined let's say zone where the steel is placed. Maybe it's always wet. I don't know. What do you think about this? Is it really atmospheric, or maybe more something like really aqueous corrosion taking place?
Yeah, it's a very good question. Currently, there is an Australian standard that is called atmospheric corrosivity zones that is used and referred to in the masonry construction standard. So the government and current standard committee call it atmospheric, but I completely agree with you, Philippe. I think there's more going on there. I was hoping Carmen or someone from the concrete reinforcement corrosion could elaborate perhaps on what they think the mechanisms could be taking place, but very interesting question indeed. We're simulating here in the lab different microclimates that we idealize. Aqueous, complete, dry and wet, and then just atmospheric to see.
And about concrete, I was also thinking about this. Do those materials, the bricks, can be compared to concrete in terms of porosity, or do you know?
Yeah, the modern bricks is very different from these older bricks, yeah, in the building. So let's just focus on the older bricks for now. They're very, very porous. They are made or were made at the time. There's still some of them are still made today to actually maintain the heritage facade. When you repair older buildings, you basically use hand force to press mud into a brick, into a form. So you can imagine the air bubbles trapped in there as you do that.
Okay, so no more questions. So thank you again, Igor. And now I will introduce the next speaker, Dr. Xia from the University of Tianjin in China, who will talk about field corrosion monitoring in marine atmosphere by electrochemical noise.
Philippe, thank you for giving me the opportunity to talk about the work that will be done. So I'm Xia from Tianjin University. So my topic shown here is field corrosion monitoring in marine atmosphere by electrochemical noise. So what I'm going to talk about today has been published over the last few years, and 3 of which are in the Journal of Electrochemical Society and are in open access. So this is the outline for my presentation. First, I will use several slides to introduce fundamental information of electrochemical noise. Then I will talk about our work on EN applications in the field corrosion monitoring, including the measurement instrument, software for corrosion data processing, and probe and sensor design. At last, I will show some field monitoring results. So allow me to start with some slides on the fundamental information about electrochemical noise. So electrochemical noise is a general term given to fluctuations in the potential and current generated spontaneously by corrosion process. So noise sources at the metal electrolyte interface can be anodic dissolution, during pitting corrosion, localized corrosion, and fluctuations of species concentrations at the metal electrolyte interface. So as summarized in this table, there are nine measurement modes that can be used in measurement. So DRA mode is the most frequently used in field corrosion monitoring because it can measure potential noise and current noise at the same time. In the DRA mode, the electrode can be symmetrical or asymmetrical. So symmetrical electrodes incorporate 2 or 3 nominally identical working electrodes with the same surface area. And asymmetrical electrodes include a working electrode of the same material but different surface areas, and system with different materials in each of the working electrodes, the counter electrode and the reference electrode. So in this work, we used these 2 electrode systems, number 2 and number 5. So this table lists most of the mathematical method and parameters used to analyze EN data. I'm not going to introduce each of them in details, but only mention 2 of them. One is noise resistance, and the other is wavelet energy distribution. Noise resistance is defined as the ratio of standard deviation of the simultaneously measured potential noise and current noise signals. So it is inversely proportional to corrosion rate. And for wavelet energy distribution, noise signal can be decomposed into several signals named as D1, D2, D3 to S8. So D1 is a high frequency signal and S8 is a low frequency signal. For localized corrosion, the wavelet energy at low frequency is higher than that at a high frequency. Okay, now let's get right to the topic. So there are several issues when we use electrochemical noise for field corrosion monitoring. First question is how we can guarantee the long-term stability of the electrochemical instrument after it is exposed to outdoor conditions. And second one is what kind of sensor and probes can be used. And third is how can we deal with such big volume corrosion. So this is a designed instrument for electrochemical noise in the field. So it was composed of a real-time embedded controller as shown on the right, and two self-made zero resistance emitter modules as shown on the left, and one DC power supply. So our experience showed that this instrument has been successfully worked in outdoor conditions for 6 months. The obtained EN data was saved in a USB flash drive as shown here. The EN data were recorded automatically for every 15 minutes interval, and each recording lasts for 512 seconds. The sampling frequency was set as 2 Hz. After the test, the USB flash drive was taken out and was read by a computer. Because of the data volume is large for long-term corrosion monitoring, so we edited software by using LabVIEW and the software of noise resistance and wavelet decomposition on the measured noise signal. Okay, now let's go to the section of electrochemical probes and sensors for field corrosion monitoring. So this is the electrochemical probes designed based on symmetrical electrode system. It means that we used 3 identical electrodes that are made of steels. We also designed a sensor based on asymmetrical electrode system, as shown in this picture. So the sensor incorporated 2 electrode. One is counter electrode, and the other is reference electrode. Okay, this is a monitoring result show a field corrosion monitoring, and it shows 20 days result of the two steels. One is carbon steels, and the other is T91 steels. And this figure show as shown here, humidity is low. The current noise and potential noise amplitude is very small. Only a few nano amps and millivolts respectively, indicating that the corrosion rate is significantly low. And when the relative humidity is increased to 65%, as we can see here, the fluctuation amplitude of the current and potential noise increased obviously. So therefore, the corrosion rate of the steel is significantly increased accordingly. By comparing the noise resistance for these 2 steels, we can see that the corrosion rate of Q steel is higher than that of T steels. Okay, so we can use wavelet energy distribution to identify the corrosion form. So the corrosion form of these 2 steels, we can see the low frequency corrosion forms, and the high frequency higher than that of T steel, whereas the low frequency energy S8 of Q steels was lower than that of the T steels. Okay, we also use 2 sensors as shown in figure B. We use 2 sensors to monitor atmospheric corrosion of Q and T steels in marine atmosphere. So this is a picture of the field measurement. And figure B, as shown here, figure B shows that shows 2 sensors were placed on the surface of T and Q steels. This is a monitoring result, the noise resistance. The noise resistance of Q steels is 10 times lower than that of the T. So it means that the corrosion rate is very high. Okay, so I'm going to present my conclusion now. So we established a noise measurement system for field corrosion monitoring, and we designed electrochemical probes and sensors and software for batch processing corrosion data based on lab view. And based on the wavelet analysis results, the uniform corrosion and localized corrosion can be well identified by comparing the wavelet energy distribution. And the last point is average corrosion rate can be quantified by using noise resistance. Okay, last page. So I would like to thank our collaborators. So I'd like to mention Shi Song in our group, and François Yu from Sorbonne University, and Jingli Luo and Yasha from University of Alberta. And thank you so much, and thanks for your attention.
Thank you, Dr. Xaya, for this very interesting talk. I can't see no question in the Q&A panel, nor in the conversation. But I can see a question. A question from Andreas Ein. I recognize noise resistance in megaohm range on rusted steels. How can it be, since noise resistance should be comparable to polarization resistance?
Okay. This is a very good question. Since noise resistance should be comparable, yeah. Yes, we have calculated the polarization resistance of the two steels. It is comparable to the noise resistance of these two steels. Yes, we have calculated the resistance.
Okay. I have one question. Do you know of a type of sensors for atmospheric corrosion? And my question is, if there is any of a type of sensors, does the electrochemical noise measurement sensor doing better than other methods? Could you?
Oh, okay. Okay. In my opinion, I think the advantage for, well, I can tell you why I choose the electrochemical sensor. I think because atmospheric corrosion is an electrochemical process is an electrochemical process. So I used electrochemical method to measure the atmospheric corrosion. I think it has advantages.
Yeah. Okay. Okay. Thank you. Thank you again. Okay. No more questions. Okay. So I will now introduce the next speaker. That is the last speaker for the marine corrosion session. He is Clément Génin, who is a PhD student working with me in La Rochelle. So Clément, it's your turn.
So thank you for listening to me. I'm about to present my work about cathodic protection of carbon steel in the tidal zone through the analysis of the evolution of the mineral layer from the immersion zone to the splash zone. This is a study made at the LASI laboratory in collaboration with Normal Group Research. First of all, there is an industrial interest, which is to quantify the effect or the efficiency of cathodic protection in the tidal zone in order to decrease the installation and maintenance cost of anti-corrosion paints. From the research point of view, a previous article showed that cathodic protection could be efficient in the tidal zone, even though the steel surface is not immersed. This is the spread out cathodic protection. The tidal zone implies to take into account some various cases, such as the first one, where the sample here considered is, is totally immersed, and then the cathodic protection works. The opposite case exists too. Here there is no water, so there is no corrosion, but there is no cathodic protection neither. Another case is when water film is persistent on the steel surfaces, and then the ionic conduction is ensured, and the cathodic protection is ensured too. This is exactly what the spread out cathodic protection is. When this water film is discontinuous or too thin, there is no cathodic protection. So there is corrosion. Corrosion is active. Okay, so to understand better the phenomenon involved in the tidal zone under cathodic protection, it's important to have an overview of the corrosion phenomenon that occurs in this area. So first of all, the constant immersion implies the production mainly of green rusts, while the cyclic immersion enhances the production of magnetite. Cathodic protection, on the other hand, implies an increase in interfacial pH, which leads to the precipitation of aragonite, calcium carbonate. On the other hand, brucite could precipitate with higher pH than 9.3 and lower potential, cathodic potential, which are rarely achieved through galvanic cathodic protection. This study focuses on structure as this one, which is presented, where the geometrical continuity between the samples is ensured to allow the residual film formation along the whole structure. Here, this is the real structure exposed in the La Rochelle Atlantic port, facing north. This is an important information because the drying conditions are disfavored because of the rarely facing sun. Each component of this structure is individually connected to the anode and can be connected to a potentiostat to perform some electrochemical measurement, which are not presented here. As I said before, this is a galvanic cathodic protection device using an aluminum zinc indium galvanic anode. And to collect the results, the sample surfaces have been scrubbed to collect the whole mineral layer, which have been then crushed to perform XRD analysis. The samples are named as follows: 111 because this is the first column of the first section and the first sample. The following one is the 112, and so on and so forth. Okay, let's start with the results. The first coupon presented here is the 132, which is representative of this area, with a net gauge immersion rate of 84 to 90%. This immersion rate is calculated over 1 year for the time of immersed phase. The diffractogram obtained on this coupon present a lot of calcite, which comes from the shells. Marine sediments are also found in large quantity and with many compounds such as quartz, kaolinite, hyalite. But there are also aragonite and magnetite, which are both compounds of cathodic protection. Aragonite because of the calcareous deposit, and magnetite is one of the residual corrosion products under cathodic protection. This is a similar feature as efficient cathodic protection sample in constant immersion. Higher in the tidal zone, in the mid-tidal zone, this coupon is presented, representative of this area, with an immersion rate of 45 to 52%. The obtained diffractogram is presented here, with still a lot of calcite which comes from the shells. Aragonite is present too, such as an indicator of the cathodic protection, and brucite is detected too, which was really unexpected. As I said before, brucite requires high interfacial pH to precipitate and really low cathodic potentials. Indeed, with the galvanic anode, it's rarely achieved. So the hypothesis of the precipitation of this brushite is because of the residual film. If the residual film persists and the cathodic protection is efficient, then H- ions continue to be produced at the cathode surface without renewal of electrolyte, which is an important point. Then, if there is no renewal, the pH continues to increase and increase and increase, and we can achieve pH over or superior than 9.3, which led to the brushite precipitation. Magnetite is still detected, and pyrrolite is found also, or could be found, because we have only one peak to detect it. Pyrrolite is a characteristic product of the cathodic protection, which has a formula similar to the grain rust with magnesium ions in their structure. Here on the sample, there are more calcareous deposit products than corrosion products. So through this and the persistence of brushite, we may assume that cathodic protection is efficient up to this level of the tidal zone. The next sample presented is a bit higher too. Here, still representative of this area, from 90 to 26% of immersion rate. And here, magnetite is a main compound detected, which is a characteristic corrosion product of the cyclic immersion. Goethite too is detected, which indicates large flow of dioxygen, and pyrrolite again. Calcite is still detected from the shells. Aragonite and brushite are again detected, which indicates that cathodic protection is still a little bit efficient here. But there is an opposite ratio. I mean that corrosion products are more present, are predominant above calcareous deposit, which led to the hypothesis that cathodic protection may not be efficient in this zone. This is a transition zone between this slide and the previous one. The highest part of the tidal zone is here, representative of this part, which sees really few immersion rate from 4 to 6%. And there, goethite is a predominant corrosion product, which is an oxo hydroxide, which indicates a huge, again, a huge flow of dioxygen. Magnetite is still detected, and aragonite is detected too, which indicates that cathodic protection could persist during the immersed phase. Aragonite, lepidocrosite is detected, and akaganite is detected too, which is an indicative corrosion product of chloride-enriched environment. Indeed, this corrosion product requires source saturated in chloride environment to precipitate, which occurs during the evaporation of the droplets in the splash zone. According to this feature, we could suppose this sample is exposed to the splash zone and with some efficiency, really rare of the cathodic protection during the immersed phase. To conclude, the varying composition of the mineral layer along the tidal zone implies or is indicative of the varying mechanisms we encountered. From the low part of the tidal zone, this is comparable or similar to a constant immersion, while the upper zone is really similar to the splash zone. The important key of this, the key point of this presentation is that brushite have been detected here, which were not expected. Through this and the ratio of calcareous deposit above the corrosion product, we may assume that cathodic protection should be efficient up to 50% of the immersion rate in the tidal zone. This hypothesis have to be confirmed with further studies, such as the quantification of the phases present here via the XRD analysis. Micro-Raman spectroscopy should be led to to understand better the stratification and the possible presence of nanocrystalline mercury, and then to evaluate the corrosion rate in this zone. Thickness loss measurement should be performed too. Thank you for your attention and to permit me to present my works here for the first time. Thank you a lot.
Thank you, Clément, for his very nice talk. I don't see any question. Once again, in the Q&A panel, maybe I can ask you a short question.
Yes.
Yes, you said that brucite was unexpected because actually in the immersion zone there's no brucite.
Well, actually, in the immersion zone, brucite is not found, at least with the cathodic protection by galvanic anodes, because the renewal of the electrolyte does not permit the accumulation of H2- ions, which are protected here. Then the pH is increased, but not enough to achieve the precipitation pH of the brucite. So aragonite is a main compound, which is because we are still in a pH between 8.3 and 9.3 pH.
Yeah, and actually, maybe you didn't mention it, but if you go back to the first XRD pattern for Köppen 132, and there are other Köppens like this. If I remember well, we did not observe brucite at that on these Köppens.
No, brucite is not detected here.
Okay. So this confirms that brucite is typical of the mid-tide region.
Yes.
Okay.
Yes,
so,
because this is a sample that sees a lot of immersion rate, and so there is a lot of renewal of electrolyte. Then there is no accumulation of H2-.
Okay, thank you, Clément. So I think we can now end the marine corrosion session. I thank all the speakers for their very nice talks, all the participants also, and maybe I can let Charlotte speak for the organizers.
Yes, thank you very much, Philippe. So this now closes the morning sessions. We will be back at 2 p.m. Central European Time, so in 55 minutes, where we will have the 2 more sessions, and the first one will be corrosion and passivation of compositionally complex and high entropy alloys. I thank both chairs and all the speakers this morning. Thank you for your time and interesting presentations, and hope to see you all back this afternoon. Enjoy your lunch or dinner or just a break. Bye bye everyone, see you later.